Hello everyone, Mr. John here from Areteem Institute and ZIML with a practice problem from the 2021-2022 AMC 10 and 12 practice exams from the online contest portal. This is from practice AMC 10 exam and it is number 23. So question 23 on that exam here. Let's take a look at the question here. We want to find the area of the region bounded by the graph of this equation. So we have a big absolute value, and then inside that absolute value of 2x minus absolute value of 2 root 3y, and then closing that absolute value, and this whole thing is equal to x squared plus y squared. Now, we're going to erase answer choices and stuff in a second anyway, but just taking a look at the answer choices, we have, right, some 8 pi over 3 multiples, 16 pi over 3, 8 pi, 32 pi. That makes us think of circle. That x squared plus y squared also makes us think of circles. And then we have this other subtraction there. So we have a 4 root 3, 8 root 3, different things like that as well. And as I mentioned, the source of this problem is the kind of practice AMC 10 that was on the practice portal for the 2021-22 exam in this case. Okay, let's jump in then and focus on our equation and our graph a little bit here. So we have a lot of absolute values and things like that there. So we have these nested absolute values, and let's start kind of thinking about what's kind of going on with this equation. And our first question here is going to be about symmetry. So we kind of want to ask the question here, is there symmetry in this graph? And remember, we can check symmetry using the equation directly there. Remember, if we think about replacing x by negative x, right? So ask yourself, if I turn all of the x's into negative x's, well, one of the x's is in an absolute value, right? Absolute value of 2 negative times negative x is the same as 2x there. And the other one is in a square. So replacing x by negative x doesn't change anything. So this tells us that we have, right, a kind of x-axis symmetry, right? We have a vertical line of symmetry through x equals 0 there. So we have x-axis symmetry, and similar thoughts tells us that we have y-axis symmetry as well. Right, and so just very, very roughly, right, thinking about this in terms of our problem then, right, we're going to have some graph here, but then we can focus on the first quadrant, right? So let's focus on when x is greater than 0 and y is greater than 0. Because then that region is, of course, just going to be multiplied by 4. Right, so our general picture here is if we have some graph, right, in the first quadrant, right, and then that graph is going to be repeated. At least the area is going to be the same, right? So we're going to have some similar thing on the bottom, but then that all is kind of flipped over kind of that way too. All right, so we don't need to worry about that graph too much there, but the idea is we can focus on one portion and then multiply that by 4. We can focus on this first quadrant in this case. So we can focus on that first quadrant, and that is of course telling us that we have x bigger than 0 and y bigger than 0. So, right, greater than or equal to if you like as well, but let's just kind of think of this as, right, we have non-negative values in this case there. So what this does, first of all, is gets rid of those inner absolute values. We can't get rid of the total absolute values here, but this definitely gives us that we have the absolute value then, that inner absolute value 2x just becomes 2x because that's positive. The 2 root 3y just becomes 2 root 3y with no absolute value. And then this is equal to x squared plus y squared in this case. So we still have an absolute value, meaning we still have to do a couple of cases in this scenario. So, right, this is our 2x minus 2 root 3y. Of course, that's just a plus or minus for the two cases there. But let's do the first case in more detail. So if we kind of divide by 2 everywhere, if x is, let's say, greater than or equal to square root of 3 times y, then that left-hand side is positive here, right? So we have kind of 2x minus 2 root 3y is equal to x squared plus y squared. Now, putting this all on the same side then, right? Let me kind of shift the zeros around and stuff here. But let me kind of say, okay, we're going to have an x squared minus 2x. Let me leave a suspicious little bit of space there. Then we're going to have a y squared plus 2 root 3y. And then this is going to be equal to 0 in this case. And remember, we had this symmetry. We have these pies in our answer choices on the previous slide. We have x squared plus y squared. This is all making us think of circle. And therefore, right, it's pretty natural here to complete the square. So we can add a 1 on both sides to the x portion. We can add a 3, right, on the y portions there. And we pretty easily see then that we have x minus 1 squared plus y plus root 3 squared is equal to, let me write it as 2 squared there. So this is a circle. We have a circle with center of 1 negative root 3 and a radius of 2. And we're not going to do all of the details of it, but you can pretty easily see in the other case, if x is less than square root of 3y, the kind of whole picture turns the kind of reflected in a sense, and you're going to get the expression, instead of x minus 1, we have x plus 1. So everything, or not everything, just the y and x coordinates of that center swap around a little bit. So here you're going to have x plus 1 squared plus y minus 3 minus root 3 squared equals 2 squared in this case. So this gives us then another circle with radius 2, this one with a center of negative 1, positive root 3 in this case there. So again, this is first quadrant. We're going to multiply everything by 4. But let's take a look now at the graphs of these circles and see if we can start determining the area inside that first quadrant as well. Okay, so here we have these circles in this case. I'm going to erase this, but just want to mention again, we're focused on the first quadrant here. So this is only the focus of what we have there. We just want to focus on this region. I have the circles drawn in the other region, but that's not actually our graph. Our graph is just this region in the first quadrant there. Right, it's not too hard to see that both of these circles contain the point 0, 0. I guess for reference here, let me kind of just quickly label the circles here, right? So in red, we have our x minus 1 squared plus y plus root 3 squared is equal to 4. And so that means kind of this point right here is 1 negative root 3. And we have the same thing in blue, except kind of flipped around in that case. So here we have x plus 1 squared plus y minus root 3 squared is equal to 4. So that's again a radius of 2. And this point here then is negative 1 positive root 3 in that scenario there. So pretty easy to see that they both contain the point 0, 0. if you think about the distances a little bit, right? The distances between these centers is, if you use the distance formula, you're going to get the distance is 4, which is twice the radii. So everything works out nicely then, in the sense that the distance between these two centers is 4, so these actually are tangent. So one little worry you might have, that now we're kind of proving is not a worry, would be, do these circles overlap at all? Do we have to worry about any shared region inside both circles in the first quadrant? And the answer there is no. So we can just focus on what is the area in the red circle above the x-axis and what is the area in the blue circle to the right of the y-axis. We have our regions inside that first quadrant that we want to focus on here. Now there's not too many things we can do when we're trying to find areas of circles, right? We want to find this area here, so you naturally want to think about the sector. So okay, let's connect the center of our circle to our points of intersection, and then we're going to subtract off the triangle in this case. Now, here's the nice thing that we want to notice here. What is this point of intersection here? This is the point 2, 0. Meaning, what kind of triangle do we have? We have a equilateral triangle then. So we have a 2, 2, 2. All of these distances are 2 in this case. And that means we have a 60-degree angle in terms of our central angle there. So if we kind of talk about the areas in this case, right? So if we kind of label this the red region area there, we can actually calculate it pretty easily then. This is a 60-degree angle, so that is a 60 over 360, or 1/6 of a circle. So this is 60 over 360. The circle has a radius of 2, so this is pi times 2 squared in that case. And then we have an equilateral triangle with a side length of 2. Right, if you want to split this into two 30, 60, 90 triangles, more on those in a second, spoilers, but right, you can kind of figure out that that's going to have an area of √3 then there. So, right, however you do that, that's kind of basically you can rearrange that into a rectangle that is 1 by √3. And so our area here is basically 1/6 times 4 pi. And I'm not going to simplify this for reasons you'll see kind of in just a second, but we can kind of think of this as a fraction of the circle and then minus this triangle there. So let's think then about the blue area. And you probably pretty easily can see that this one is going to follow a very similar pattern in this case. So what do we have then there? So this, again, let's connect our points. So we have our points of intersection, 0, 0 to -1 √3 in this case. And then we have -1 √3 to up here. What is this point? Well, it's pretty easy to see that this point is 0, 2 √3. Now, if we're then looking for our shaded region, right, where again, this is a bigger shaded region in this case, we have more of that circle at least there, a bigger sector and everything. But if we start looking at things, right, we again have this triangle there. Now this triangle has a base on the kind of vertical base of 2 √3. So wait a second, these radii are still 2. This is a distance of 1 if we drop the altitude. These are both √3s here. So we actually have two 30, 60, 90 triangles. We actually have the same exact two triangles, just arranged a little bit differently in this case. But this is now a 120-degree sector. So using the same strategy, we have a 120-degree sector. So now we have 1/3 of the circle. And again, we have two triangles. They can be rearranged into a rectangle with area √3. So this one here is 1/3 times 4 pi, right? The reason I didn't simplify this before is we can now combine them as our final kind of step here. And 1/3 plus 1/6 is going to be a half in this case. So our final answer, and remember our final answer is 4 quadrants. So let me just put the 4 times right off the bat here. We have 4 times the sum of these two things there. So based on what I just said, right, we have this area 1/6 times 4 pi minus root 3. We have 1/3 times 4 pi minus root 3. So adding those together, we have 1/2 times 4 pi. So that is 2 pi. And then we have minus 2 root 3 here. So we have minus 2 square root of 3 in that case. So adding these, or not adding, but multiplying everything out, we will get a final answer of the total region, right? Which is kind of this loops like I kind of had at the beginning, one bigger sector, one smaller sector, right? All kind of put together there, 8 pi minus 8 root 3 in this case. And so that is our final answer to this geometry problem here. So kind of putting it all together, anytime you're doing these circle areas, you're going to end up oftentimes with sectors minus triangles and things like that there. And same thing here. So do the symmetry, take advantage of the symmetry, and then do some algebra to get your circles, and you can start working everything out from there. That does it then for this problem. If you want some more practice, either last minute or throughout the year, our ZIML site at ziml.areteem.org, also available in the ZIML mobile app, has some great archive things of AMC 10-12 exams. It also has other additional practice problems and our daily magic spells, monthly contests, other great things like that as well. If you liked this video, it really helps me out if you like and subscribe below. Otherwise, I hope to see everybody in future videos, and let us know in the comments below if you have any suggestions for problems or other things to solve and talk about on this channel as well. Goodbye, everyone.